We have just seen that Maxwell equations, in its differential form, express a certain relationship between space and time derivatives of the fields. In a compact notation, we're using certain vector operators that are called divergence and curl. We have seen how in Cartesian coordinates we can compute them mathematically, but now we're interested in having some physical insight on the meaning of those operators. First, we're going to start considering the divergence. For that, consider the present case in which you have a certain vector field A, and here we are just plotting the field lines, and then we define a volume V, which is defined by a closed surface S, and then we have the vector N, which is a vector normal to the surface S. In that situation, we have what is called the divergence theorem that sets the following relationship. It says that the volume integral of the divergence of A equals that integral. That's the surface integral of A dot product with N. But we can see that the value of this integral is just the net flux of A through S. When we say the net flux, we just mean the flow, the overall flow of A through S. Well, now if we consider that V it's a very small volume, actually V tends to 0, we can assume that this divergence is essentially constant inside that volume, and then this integral is just V times the divergence. So we can write this relationship, and then we can see that the divergence can be understood as the net flux of a vector field through a surface, through a closed surface, when that volume tends to be 0. So actually divergence just gives us an idea of either if in that vector field there is a certain concentration or if there is a net flow, then meaning that there is a concentration of field lines, or just there is a net outwards flow of field lines, or in the case that the divergence is 0, means that the net flow of that vector field is 0 through that closed surface. So if we see different cases, imagine that we are just representing a vector field, and in that case we compute the divergence in this point. Okay, in that case the divergence would be 0, it would be greater than 0 because there is a net flow of that field coming out of the surface. In that case the divergence would be negative, smaller than 0, because there is a net flow going inwards the surface, and in that case the divergence would be 0 because the net flow of that vector field is 0. When the divergence of a vector is 0, we call that field A, in that case, is solenoidal. If we try to give also some physical meaning of the curl, we'll start with the following situation. We're going to consider also a vector field A. We define a closed path C. S is the surface defined by C, and then N is a unit vector normal to S. And the direction of that vector is defined by the circulation sense along C and using the right-hand rule. So if we go around that closed path C in a counterclockwise sense, if we use our right hand, our thumb would point towards the screen, towards you, and that would be the direction of that vector N. Well, in that case, we have what is called the Stokes theorem that says that this integral, which is known as the circulation of A, that's the integral of A along that closed path, is equal to that surface integral of the curl of A dot N. Once again, if we consider that that surface is very small, it tends to 0, we can make the following derivation, in which we see that essentially the curl is the circulation of a vector along a closed path when the surface defined by that path tends to be 0. Now, imagine for instance that we have a gravitational field, and we are moving, we're doing that circulation along this path. Well, we know that when we move in this direction, the circulation is 0 because we are moving orthogonal to the movement. In that case, we are going against the field, here is 0, and now we are going along the field. But the integral along this segment and this segment will cancel. So for instance, if we are in a gravitational field, we know that this circulation will be 0. So that means that, for instance, in the gravitational field, which is a conservative field, the curl is always 0. So if A is a force field, at the end this integral is just the work done to move along a closed path. And for instance, when we have a conservative field, for instance gravity, we know that that should be 0. In that case, we say that the field is irrotational, and any conservative field is always irrotational. Now, in that case, the rotation of this field is 0. When we have a field like this, the curl is negative, just because of the sense of rotation of the field, using our right hand rule, and in that case, the curl of the field is positive, is greater than 0.